So what came from all of this information was the Schrodinger wave equation. And what the Schrodinger wave equation gave us, what's important for us to associate with that, are the orbital shapes, the mathematical probabilities of where these electrons are. And that is the quantum theory, quantum mechanics. Okay? What the Schrodinger wave equation predicted is that the electrons do not travel in nice specific orbits around the nucleus. They actually travel in something called an orbital. An orbital is three-dimensional, not planar. Does that make sense? It's a three-dimensional mathematical probability. It's not just spinning in a circle. It's three-dimensional. It's got shape. Okay? And so the orbital is that three-dimensional structure. And so quantum numbers, we have 4 quantum numbers that tell us all we need to know about where an electron is likely to be. Okay? The first one is the principal quantum number. That's the main energy level. The next one is the angular momentum quantum number, which tells us the shape of the orbital. Then the magnetic quantum number, which is the orientation of the orbital. And then the last one, the spin quantum number, which tells us which spin state it's in the positive direction or the negative direction. Okay? And then these orbitals have specific shapes. S, P, and D are the only ones I'm really concerned with that you know. S is spherical, P has a dumbbell, and D is very similar to the P orbital, other than the fact that it goes twice. It actually, whereas a P orbital is filled sort of like halves, the D orbital is one whole. Okay. Does that make sense? When you look at the difference there, you see 4 angles instead of 2 for each D orbital. Does that make sense? Okay. So electron configuration then, all of those quantum numbers tell us about electron configuration. And that will tell us we can use a chart like this to figure out figure out orbitals of their energy. This chart is basically saying electrons will fill the lowest energy level that will receive them, and that is Aufbau's principle, right? Aufbau's principle tells us that all these electrons, they'll fall to the lowest energy level possible before they begin to fill anything higher, right? Now, the next two, Pauli's exclusion principle and Hund's rule, they kind of go together. And what you're doing in lab right now, this lab on magnetics, okay, on magnetism, this is very similar to the data that these scientists were seeing. So think about this. From manganese to zinc, in terms of our lab, right? What are you seeing happen? Every additional electron, what happens to magnetism?
Well, it depends how much we are going.
Right. Okay. But if you think about the electron configuration, every time there was an additional electron, you either increased or decreased, right? You would increase as you came across the periodic table up to chromium and manganese. And then as you add one, you would fall off in magnetism, right? So what they saw then, they knew that when electrons were moving in the same direction, they would generate a magnetic field. They also knew that if the electrons were not moving in the same direction all the time, that the magnetic field would go away. They also knew that if you took a magnet with a magnetic field around it, and then took a second magnet and put it in the opposite alignment, you could cancel out the magnetic fields and have no magnetic field. Or if you line them up, you put them together, the magnetic field gets larger. Right? They knew all that. When they looked at these elements, and as these electrons were being added in one by one, they saw this increasing pattern go up, 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 and then from there, down, 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 in terms of the magnetic strength. They realized that these electrons are going into each orbital one at a time. They're beginning to line up, increasing in magnetism. Then, when they all have one, another one goes in, and that is destructive to the magnetic field and boom, 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 down they go in magnetism. Does that make sense? Okay? We are in lab right now really demonstrating Hund's rule and Pauli's exclusion principle. We are seeing that if you stack these electrons into orbitals where they're all going in the same direction, you get magnetism. Just like magnets, just like anything else, just like electricity, just like electromagnets. But if you start putting one in that's in the opposite direction, you start to take away from the magnetic field. Does that make sense? Okay? So we're really connecting lab with what you're learning in the book for chapter 4. I mean, probably more so than I think you may have ever done. I mean, we are really doing the experiment that they did and that they learned this. Okay? Or one of them. This is one of the probably hundreds of different methods to reference. Okay? And so now I think at this point, all this arrow up and down, you get this now, right? We're representing the spin number. Okay? Electron configuration notation, 1s2, 2s2, right? You understand all of that. Noble gas notation. You guys told me that you already know how to do that. And why do we use the noble gas in terms of electron configuration? It shortens it, but what is it about a noble gas?
Their P and S orbitals.
They're stable, but what is it about their electron
Their
configuration?
P and S orbitals are both filled up.
It's full, exactly. The orbitals are full. So if we stop there and just bracket that one in, we can assume that everything up to that point is full. Okay? Why is it that we're concerned with the valence shell? What happens there?
It changes reactivity.
That changes the reactivity, and it changes the properties, right? The whole thing about magnetism. That's based on the electron configuration, not of the inside energy levels, not of 1, not of 2, not of 3. Only of 4s and 3d, the outer energy level, right? Does that make sense? Okay. Good. And that's what this is, right? An explanation of the arrows. Good.